Good afternoon, class. In today's video, what I wanted to do was to go over light, and not just light, but how it bends and also how it reflects. So this video is going to be kind of intensive when it comes to the amount of information that I'm giving. So that's why I put a few notes over here, and I also made sure to, I'm trying to stand off center of the frame, because what I want you to do is that if at any point that you start to feel confused about this, or you're kind of not sure about what because there's so much information here. If you ever need to pause this video at any point and just read what I've written on the board over here, that's fine. Feel free to do that at any point. So let us continue with how light works. So light, as we've gone over in other videos, light is both a particle and a wave. This video does not focus on light's wave-like properties. That's more for the modern physics side of the class. This video focuses more on light as a photon, which would treat it as a particle. So that's why if you notice that some of the ways that light is behaving in this in this lesson are more or less particles, then you are correct in that instinct. So let us go through the two ways that light gets transmitted and the way light behaves when it interacts with other objects. So there are two ways. The first way that light interacts is through reflection. And like you probably have learned from looking in a mirror, reflection is when light hits a mirror, hits an object, and bounces off of it. This can also be broken up into other forms as well. For example, part of my shirt is red, so that would, one way that you could think of it as the light is reflecting, so the light from above, around the room is hitting my shirt, and when it hits the red part of my shirt, it absorbs all the other colors except red, and it re-emits those colors. So it's basically reflecting the red color off. Or if you want to look at it like this, all of these words here are written in blue ink, but it also could, the other way to think about it is that the light is hitting this board and is reflecting back to you only the color blue, based on wherever I've put the ink from the markers, the markers on the board. So that's one way to think about how reflection goes. Now there is a law and an equation that governs those reflection property, and so that would be the law of reflection, which states that the angle of incidence is equal to the angle of reflection. Now, of course, it is important to figure out where that angle is and all of that. So I decided to draw a picture here. So we're going to assume that this this line over here is the mirror, and you've got a light particle coming in this way and leaving this way. There is a dotted line over here. I don't know if you need to be able to pause that video to see it, that's fine too. But there's a dotted line over here, and that's what we call the normal. And this normal is not always necessary. This one is nice because it's exactly perpendicular. I mean, it's going straight up, so it looks like it's a straight up kind of imaginary line. It's not. There's no actual place where you can see a normal line coming out. It's imaginary, but it helps us do our calculations. This is always when So when the light hits, it always hits at on the surface of a mirror. You can always focus it down so that it becomes a flat plane. Even if your mirror is, like, say, curved or something like that, wherever the light hits, that is if you focus in on that part of the mirror that it hits, that's where the angle of incidence is going to be. And even though it may not be straight up this way, it might be coming out maybe at an angle like this or something like that. You can still, it doesn't have to be straight up. It could always be at any angle that you want, as long as it is perpendicular to the surface that it is being reflected off of. So for those of you who are more on the mathematical side, one thing to note is that normal refers to perpendicular. So if you've heard perpendicular, which is a 90-degree angle, in the mathematical term for that is normal. So if you want me to find a video on the etymology of why normal means perpendicular, I can do that. Let me know. I can make that video later. But for now, that's just kind of the way it is. Somebody decided that was the case. Okay, So that is the law of reflection. Now the one thing to keep in mind, and this will be true for refraction as well, the angle of incidence is not dependent on the plane of the reflecting surface. Okay, it is dependent on where the normal is. So the angle of incidence is taken from the normal on, and out, and the angle of reflection is taken from the normal, to the path of the light. So that it's measured from the normal to the light beam. So that's something to consider. That's a very important consideration. We're going to be doing the same thing here in refraction. Okay, so let us go on to the second way that light interacts with a different medium, or whenever it interacts with something, and that is called refraction. Refraction is when light bends. So if light, for example, if you've ever seen light entering water, or if you've ever seen light sources that are inside water, like in a pool or something, you'll notice that they'll sometimes, the image is not always clear, and it's a little bit distorted. And the reason for that is because the water's surface, because it's shifting like this, can distort where this normal line is, and so therefore the angle at which the light from the lamp at the bottom of the pool might be coming out towards your eyes. So this one is going to focus, for this example, we're going to go from the idea that the light is coming this way and is bending into the water. So we're starting with an index of refraction of air. With a medium of air, and we're going into a medium of water. This will be important in a little bit. First, I have to introduce this concept called index of refraction. Now, again, this is another word. Why is it index? Unfortunately, I'm not entirely sure. Again, I can make a follow-up video on the etymology. If you're interested, let me know. But the index of refraction simply refers to how light will bend in a vacuum, or compared to a vacuum. So in a vacuum, the index of refraction is just simply 1. And so everything else, you get different numbers because light will bend slightly, whether it's a little bit or a lot when it comes to, when it interacts with a different medium. And that medium could be air, it could be water, it could be glass, or it could be diamond. And of course, everything in between. So I just want to make sure that that's fairly conceptually clear. Now, there's a law that governs how the light bends, and that's what we call Snell's law, which is right over here, which is n1 sine theta 1 equals n2 sine theta 2. Basically, what that means is that the angle of the light as it goes through a medium will depend on not just the medium itself, or the index of refraction of the medium itself, but the angle that it came in at as well. And of course, these angles are all taken with respect to the normal. So whether that's the normal coming in or the normal going out. Now, of course, this could always go back the other way as well. So all of these, both of these examples are focused more on light coming this way from a lower index of refraction to a higher index of refraction. And if you want to know, the index of refraction of air is different from water. Air is about 1.0079 or so. Water is about 1.33. You can actually measure that yourself if you ever are interested in trying to actually obtain this result. It's actually not that hard to do if you just take a tub of water and put stick something like a ruler inside of it. But this is going from lower index of refraction to higher index of refraction. So I wanted to put a couple of notes here. For the first note, that the light will always bend towards the normal when it's going from a lower index of refraction to a higher index of refraction. You can kind of think of it kind of like this. Like if you're, let's say you were running and all of a sudden you were on a sidewalk that was dry, and all of a sudden you started running onto a muddy patch of dirt, but you came in at an angle. To make sure that you don't slip and fall, one of the things that you might do is you might slow down, so you might not take as big steps when you're running, when you're transferring your body from, or when you're transitioning from the dry, concrete pavement to the muddy grass. So that's something you might want to consider. That you would start to veer off. You might have thought you were going straight, but there is a slight pull towards this side because your legs didn't hit the ground at the exact same time. One of them will be traveling a little bit slower than the other, just to make sure that you try to keep as much speed as you've got while you're running on it. That's one way to think about it. And that's why light will bend towards the normal. On the other hand, if you're going the opposite way, you're running on, let's say, a muddy patch, and all of a sudden you're going you're running onto dry concrete, you would actually have to speed up your legs, one leg versus the other, just at least in that initial adjustment before you keep going straight. And so that would be my second note, that if you're going from a higher index of refraction to a lower index of refraction, it will be the opposite effect. You will be the light will bend away from the normal. Okay, so if you're going from here to here, the angle will increase. Okay, so that's what I wrote over here. And again, if you need to look at that, you can. So the last part I wanted to talk about before I get to, of course, the thing that we're always looking for when it comes to light, which is rainbows, is what we call the critical angle of a material. And this is the angle at which you cannot see, the light does not go through anymore. It actually just stays along the surface. That's why I drew it over here, where there's the normal here, and then there is a right angle over here, because the light hit the surface and didn't come out of the surface into the next surface. You actually can have an example of this. Is it as if you've ever gone to a pool and there's a light at the bottom of the pool. If you've ever walked at a certain angle away from it, at some point you won't be able to see the light anymore. In fact, if you go under the water, at some point you'll actually see the light from maybe across the pool being reflected back into your eyes as if it was bouncing off of a mirror. That's because after the critical angle, the light will bounce off and will follow the laws of reflection afterwards. So what is that critical angle? We're using Snell's law again, and all we're doing is we're solving for what that critical angle might be, because the critical angle is when the second angle is going to be 90 degrees. And of course, the sine of 90 degrees is 1. So when we solve for the critical angle, we find that it's the arc sine of n2 over n1, where n2 is going to be a lower index of refraction than n1. So just keep that in mind in case you're like, well, what if n2 is bigger than n1? That doesn't happen. It won't happen, because the arc sine of that will give you an error. So something to keep in mind. Now, the last point that I wanted to make while I wrap up this video is about rainbows, because some of you might be wondering, okay, so how do rainbows form? And what's the mechanism behind that? And it actually comes back to refraction. What happens is you've got the sun's light, which is white, which means it has all the colors of the rainbow all together in one beam. When it hits the rain, what will happen is that it'll split into various colors, kind of like a prism. It'll split light into all the various colors of the rainbow, for lack of a better term. And the reason for that is because each wavelength of light actually has a slightly different index of refraction. And so when you have enough water, which is in this case is the rain, the sunlight hitting the rain at a certain angle, it'll split all of the different colors of the rainbow, and they'll split up like this, and then they will reflect off of the rest of the rain droplets and come back to our eyes in the form of a rainbow. And also a little bit of a bonus fact here, rainbows are actually circular. You just can't see them because when we're here on the ground, they look like this like semicircle, but it actually goes all the way around. You just can't see the bottom part of it because the ground is getting in the way of that. So thought I'd throw that out there. If you ever try it, you can actually try this. If you take a gardening hose, shoot water up in the air and let the sun hit it, you'll actually start to, if you get the right angle, you'll actually see a full circle rainbow. You can also see this on airplanes if you have the right conditions. So something to look forward to on your next airplane trip. So that concludes how to think about light and how it interacts with the world around it. So good luck in your studies, and may the force be with you.